Picture a calendar with only 2 mornings on it. You wake up, the sun climbs, and by the time it sets and rises again, an entire year has already passed on the calendar behind you. That isn't a riddle. That's an ordinary Tuesday on Venus, the planet next door, close enough that it's the brightest point of light in your night sky. Here's the part that doesn't sit right once you check the numbers. A single day on Venus takes longer to finish than a single year on Venus. Say that plainly, and it sounds like a typo. A day is supposed to be a small unit, and a year is supposed to be the big one, built out of many days. The way it works on Earth, on Mars, on basically every planet you'd sketch in a school diagram. Venus breaks that ordering entirely. One full spin on its axis outlasts one full trip around the Sun. To understand how a planet ends up like this, you have to start with how anyone even measured it, because Venus never lets you see its surface directly. Venus is wrapped in cloud permanently, a thick blanket of sulfuric acid and carbon dioxide that reflects sunlight beautifully and hides everything underneath. For most of history, nobody could time its spin at all. That changed in 1961, when Richard Goldstein at the Jet Propulsion Laboratory bounced the first clean radar echoes off Venus using the Goldstone antenna in California. Radar goes straight through the clouds. By 1963, Goldstein and Roland Carpenter had used that returning signal, publishing in Science, to catch something moving on Venus's actual solid surface, and clocked it. The number that came back was strange twice over. First, the period, close to 240 days, refined over the following years to 243, longer than Venus's own calendar year of roughly 225 days. Second, the direction, backward. Venus turns clockwise when viewed from above its north pole, the opposite way Earth, Mars, and most of the solar system spin. Stand on that surface, and if you could ever see through the clouds, the sun would rise in the west. Modern radar has only sharpened that original 1963 measurement. Using 15 years of tracking radar speckles bounced off Venus between 2006 and 2020. From facilities including the Goldstone dish and the Green Bank telescope, Jean-Luc Margot's team, publishing in Nature Astronomy in 2021, pinned the sidereal day at 243.0226 Earth days, against an orbital year of 224.7. The gap is real, precise, and not a rounding error. It gets one layer stranger once you ask what a day even means while standing on the ground. Because Venus is both spinning backward and orbiting forward at the same time, those two motions partially cancel out. The result, measured from one sunrise to the next, a Venusian solar day is only about 117 Earth days, roughly half of the planet's own year. A hypothetical visitor standing on the surface would watch the sun rise in the west only about twice during a single Venusian year. So the honest headline has two parts that don't contradict each other. The planet's full physical rotation, floor to floor, genuinely takes longer than its orbit. And from the ground, sunrise to sunrise, the math folds differently because the spin runs backward. Both numbers are real. Neither one is the trick version of the other. The obvious next question is why a rocky planet, roughly Earth's twin in size and mass, would end up spinning this slowly and backward in the first place. One leading answer doesn't involve a collision at all. In 2001, Alexandra Correia and Jacques Laskar, publishing in Nature, modeled what Venus's dense atmosphere does to its spin over billions of years. Their case, Venus's thick carbon dioxide blanket gets heated unevenly by the sun, piling up mass on the day side in a way that creates a slow twisting force, a thermal tide acting on the whole planet. Run that force forward for long enough, they showed, and a planet with an atmosphere this heavy naturally settles into one of only 4 possible final rotation states. 2 of those 4 states run backward. Correia and Laskar's chaotic evolution modeling found that, starting from a wide range of plausible early spins, Venus's atmosphere alone could nudge the planet toward exactly the slow, retrograde rotation observed today. No violent event required, just an ordinary dense atmosphere and enough time. It's a quiet mechanism, no explosion, no scar, just sunlight and gas pushing patiently on a planet for most of its 4.5 billion-year history. Not every researcher is satisfied leaving it there. A competing case has come back with more force recently. A giant impact. In 2025 and 2026, teams including Cedric Gillmann at ETH Zurich ran dozens of detailed collision simulations. An object roughly a tenth of Venus's mass striking at a steep angle, testing whether a single ancient hit could flip or reverse an earlier, faster spin. Their results, a wide range of impact scenarios, land on a final rotation consistent with the Venus we measure today. Here's the honest complication neither camp can fully close. Unlike Earth, where a giant impact left the Moon as permanent, unmistakable evidence, Venus shows no obvious giant crater, no companion moon, nothing pointing straight at one violent day in its past. Defenders of the impact idea note that Venus resurfaced itself through volcanic activity roughly 500 million years ago, an event that could have erased older scars entirely. Critics note that's also exactly the kind of argument you can't test. Both the slow tide story and the sudden impact story remain live, published, competing explanations. Nobody has proof that rules the other one out. What Margot's 2021 radar campaign adds isn't a verdict on which origin story is correct, it's proof the spin is still moving today. Across those 15 years of measurements, the rotation period wasn't perfectly fixed. It varied by about 20 minutes, a shift the team traced to Venus's atmosphere, trading angular momentum with the solid planet beneath it in both directions continuously. Whatever set that backward spin in motion billions of years ago, the atmosphere is still actively rewriting it in real time today. That atmosphere is doing something else entirely, one level up. The solid ground beneath the clouds turns at a crawl, under 7 kilometers an hour at the equator. The cloud tops above it do not wait for it. Data from JAXA's Akatsuki orbiter, tracked by researcher Takeshi Horinuchi and colleagues through cloud motion imaging, showed the upper atmosphere circling the entire planet once every 4 Earth days, near 300 kilometers an hour, roughly 60 times faster than the ground it's floating over. 2 layers of the same planet, moving at wildly different speeds, barely coupled to each other. The surface takes 243 days to turn once. The clouds directly above it lap the whole planet in 4. It's called atmospheric superrotation, and Venus runs the most extreme version of it found on any planet in the solar system, a detail that matters beyond Venus itself. Researchers studying slowly spinning, tidally influenced exoplanets around distant stars now use Venus's superrotating atmosphere as their nearest working example. Step back and look at what all of this adds up to. Venus started out close to Earth's twin, nearly the same size, nearly the same mass, built from similar material in the same region of the early solar system. One planet ended up with oceans, plate tectonics, and a 24-hour spin. The other ended up wrapped in acid cloud, crushed under 92 times Earth's surface pressure, hot enough to melt lead, tipped nearly upside down, and turning so slowly that its own atmosphere effectively runs its weather system on its own separate clock. None of that came from one single cause. Its slow atmospheric tides, patiently pushing for most of 4.5 billion years. It's possibly an ancient, unproven collision layered on top. It's a runaway greenhouse effect that built the crushing atmosphere doing the pushing in the first place. Pull any one of those threads out and you get a different planet entirely. Maybe one closer to Earth than to the Venus in front of you. Which brings you back to that impossible-sounding calendar. It isn't a trick of language or a rounding quirk. It's the direct, measured consequence of a planet spinning backward slowly enough that its own axis loses the race to its own orbit. 2 competing explanations for why, published years apart, neither one proven, both still standing. And an atmosphere overhead that hasn't finished moving the goalposts, still trading momentum with the ground below it every single year that goes by. So the next clear night, find that bright point low in the sky, brighter than any star, and remember what's actually happening underneath those clouds. A world built from nearly the same blueprint as this one, still spinning through a day that outlasts its own year, still arguing with itself about how it got that way. Curious Nova will be back with the next one soon.